Welcome everyone to the MSO-19 primer. Today we will learn about the various functions of the MSO-19 by probing around an Arduino. First off, here's an Arduino, and so are these. The difference is this little USB to serial converter. To get around the requirement for that converter, a few companies such as the Tinsy, Arduino, Adafruit, and Arduino got rid of it by using a amp mega with a built-in USB. But that introduced a problem. Pin 13 that traditionally uses a status pin is no longer valid on these boards. For example, the Tinsy is mapped to pin 11. So let's get going. We're going to do a little hello world for the hardware guide, which is the blink. We're going to turn an LED on and off. Go to examples, basic, blink. Bring up the code. As you can see, the blink code, it's already set up for Arduino for Tinsy 2.0 with a 16 meg oscillator. Download the code. And we got nothing. Why? Because we have to map it to pin 11. Right here it says pin 11. Try again. We have a slow blink. So let's speed that up a bit. So it's blinking at about 5 Hertz, and we start seeing that on the scope side. And let's crank it up a bit on time. Let's see what the time is. Let's set the scope to trigger on normal. It's on the rising edge, 2.5 volts, which lengths right here. Time between cursor A and trigger cursor, it's 100 milliseconds, which is what we have here. The falling edge from A to B, A minus B, it's another 100 milliseconds. And we can move B by moving our cursor here, hold down the B key and click. It's pretty fast to bring it in. For example, you want to bring it over here, boom, it's here. Don't have to drag it. Alright, let's speed this puppy up a bit. 1 millisecond on, 1 millisecond off. Okay, it's too fast to see. Let's raise the rate. So how fast are we running? Well, just do some measurement. Hit setup, go to measure, frequency, go to entire buffer, hit done. Saying that we got about 500 Hertz, which is 2 milliseconds, 500 Hertz, that's about right. And if you actually want to see this, go on the FFT and you'll see that it's running at 500 Hertz. And the harmonic comes in at 1.5K, and then the second one is going to be at 2.5K. Okay, back to time series data. Let's send this signal to the other LEDs I have set up. Remap it to pin number 10. Now we have the green light going, and it's just gonna go because it's so fast we can't see. Scope stopped. Why? Because the signal is on the logic channel, but we didn't tell it to trigger on logic. So again, just to see what's going on, let's click auto. We got data over here. Crank it up a bit. It's jittering around, so let's set up a trigger condition. Logic. Right now it's all don't care, false or true, still moving around. Set it to go for condition of 1. And put normal. Now we have a lock. Move it from true to false. Now we're on the falling edge. Let's set a second LED up. Always define the pin mode. We'll turn the second LED on after the first LED goes on, and we'll turn it off before the first LED goes off. Ah, forgot to define the name. So you see two LEDs on, and if you look on the scope side, it just looks like it's on. So let's crank this up a bit. 200 megasamples per second. So how long is the on time? It's the time between instruction cycles. From instruction cycle, from the one digital write to the next digital write, we're coming at about 1.75 microseconds. And if we go to the falling edge, and we can see that again, it's running at 1.75 microseconds. Let's go back to the true again. So how many clock cycles does it take to execute that? Well, let's see. Let's take the scope probe. We're going to measure the oscillator. See the little waveform up here? It's saying it's 16 meg. Go to FFT. Nice clean peak at 16 meg. So if we measure from this trigger cursor to cursor A, if we pause and count, we'll see 27 cycles. We can go to setup, and we tell it to measure from A to trigger, and tell it to count cycles. And we see it's coming around 26 cycles. It's exactly what we wanted to see. Well, that's it. Thank you.